So in C, we want to show that given that x is equal to k, the Lth moment of theta actually does not depend on the a priori distribution of theta either. And this is a very interesting result in the sense that normally we say, assume that theta is such and such distributed. Then, given that we have some data x, then theta will be so and so distributed in another way. We more or less uh, expect the uh, a posteriori distribution, which is the distribution of theta given x. We expect that distribution to, in some way, reflect upon the a priori distribution, which is the distribution of theta when we don't know x. However, the funny thing in this exercise is when you only have one claim number, and you just have one policy, and x given theta is Poisson distributed. Well, funny thing, the a posteriori distribution of theta, or at least its moments, do not depend on the a priori distribution of theta at all. Or I think it's funny. You might not think it's funny. Anyways, we want to show this result, and the proof of this result does not create that much understanding. It's just technical nonsense. So let's just try to calculate from this way here a little bit, and try and see what we get. So we see that the product of the Bayes estimators, mk plus 1 plus I for I going from 0 to L minus 1, well, that, well, we do have, sorry, this L should be greater than equal to 1, and we have some implicit assumption that L should be non-negative integer, or it should actually just be a natural number. So this thing here is by definition equal to, so by definition of the mk plus I, this is equal to the mean value of theta given x being k plus I, right? Now I can use the definition of mk plus I that I found in the earlier exercise instead of this, because I actually have some extra knowledge about the mk plus I. I know that they do not depend on the distribution of theta. I can just write them as k plus I plus 1 multiplied by the probability of x being k plus I plus 1 divided by the probability that x is equal to k plus 1. Okay, so what is the next part I can do here? I can try to split this product up into two products. So I have L terms of these things. So for I from 0 to L minus 1, the product of k plus I plus 1. And then after that, I have another product of these things, which is the probability that x is equal to k plus I plus 1, divided by the probability that x is equal to k plus 1. Now I can look at the first thing here and kind of notice that essentially what I have is the product of numbers k plus 1 to k plus 2, k plus 3, k plus 4, and so on, all the way up until k plus L. So what I have here is k plus L factorial, which is the product of all the numbers from 1 up to k plus L. And then I have to remove the product of all the numbers from 1 up to k, right? Because the first term in this product starts with k plus 1. So I have to divide by k factorial. Now, if I look at this product here, what I have for I equal to 0 is just k plus 1 down here, and wait a second. This should be k plus I, sorry. K plus I, yeah. Is k plus I down here, and k plus I plus 1 up here, so I have k and k plus 1. When I is equal to 1, I have k plus 1 and k plus 2, and so on. So actually, everything sort of telescopes. I can just write this up. The first term is the probability that x is equal to k plus 1 multiplied by the probability that x is equal to k. And for the next term, I have the probability that x is equal to k plus 2 divided by the probability that x is equal to k plus 1, and so on and so on. It continues until I reach the L minus 1 here. So it will be the Lth term where x is equal to k plus L divided by the probability that x is equal to k plus L minus 1. So the terms that cancel are all of these terms that are in here, and the only terms that remain are these two terms here. So essentially the product of the MKI that we're looking at can be written as k plus L factorial divided by k factorial multiplied by the probability that x is equal to k plus L divided by the probability that x is equal to k. Now, what can we use that for? Well, now at least we can say, since we know that this expression is equal to the expression that we wanted to show that the Lth moment of theta given x equal to k is equal to, then we can at least state that it suffices to show that the mean of theta to the L given x equal to k is equal to, well, let's just call this star, is equal to star. And this is a lot easier to show than the thing above. So let's just start calculating. So by definition, the mean of theta to the L given x equal to k, well, that is given as, since we have the density of theta given x equal to k, well, then this is just equal to y to the L multiplied by the density of theta given that x is equal to k. And then we integrate this with respect to y from 0 to infinity. That is just how we always find the mean value of the function of a stochastic variable. You integrate the function multiplied by the density of that stochastic variable. Now we can plug in the density function that we see here. And what we get is we can take out the probability that x is equal to k here. And we can also take out the k factorial. So the 1 over k factorial. And we have to keep the rest inside. And the rest that we have inside is f theta of y multiplied by e to the minus y to the L plus k dy. Now, what we can do now is notice that if I divide inside here by k plus L factorial, then I can multiply on the outside by k plus L factorial. And what I can notice furthermore is, in the same way that I recognize the probability of x being equal to k plus 1, I can also recognize that this is just the probability that x is equal to k plus L. And hence I have shown that this expression, the mean of theta to the L given x equal to k, is equal to this expression, which is exactly the same as my star expression from earlier. And the star expression was equal to this thing, which was what we wanted to show. So this is now done. So this was equal to the product to L minus 1, phi from 0, mk plus I. And then we are done. Now, if you felt that this went a bit fast, if you're asking, how did this happen? Then try to write up the probability of x being equal to k plus L by conditioning it on theta and then taking the expectation. Then given theta, x is Poisson distributed, and then we can calculate this mean value. So we integrate with respect to y and multiply by the density of theta. Then given theta equal to y, this probability comes from a Poisson distribution with parameter y evaluated in L plus k. So this is where the mysterious probability here came from, just in case you were wondering.